Typically, as we go through and solve equations, we just kind of do steps and don't really think too much about what steps we're doing. But every step that we take when we're solving an equation or going through some process has a justification for it. And so we're going to look at those justifications, and we're going to look at beginning to try to solve equations and knowing exactly why each step that we do works. This is a preliminary thing to when we get into proofs. So in this class, we're going to start getting into proving that things are true or proving that things are false. And in order to do that, we need to be very particular about why each thing that we do works. So we're going to start doing that with equations, and then we'll move into other types of proofs. So we have some properties here, algebraic properties of equality. We're going to use A, B, and C as variables. A, B, and C are just real numbers, any numbers that you can think of. So the first property is the addition property. So if A equals B, that means if A and B are the same number, then if we add C to A, that would be the same thing as adding C to B. So if A and B are the same, and then we add C to A, it's the same thing as adding C to B. So we can say that's equal to B plus C. So this is how we solve equations. We can use this property when we're solving equations. The reverse of that would be the subtraction property. So if A equals B, then if we subtract C from A, that's the same thing as subtracting C from B. Multiplication property. Again, if A and B are equal, then if we multiply C by A, that's the same thing as multiplying B by C. And then division, same thing. If A and B are equal, then we can divide, if we can divide A by C, that's going to be the same thing as dividing B by C. Now there's this piece right here, as long as C is not equal to 0. So we cannot divide by 0 in mathematics. Dividing by 0 breaks mathematics. We can't do that. It causes bad things to happen. So as long as we're not dividing by 0, this division property holds. And then the last one, substitution property. So if A is equal to B, then we can substitute A for B in any equation. So we can just, if A and B are equal, we can take A and just replace B with A. Let's look at solving something now. Example 1, we've got space for the equation, space for the explanation, and then space for the reason. So we're going to start with the very beginning here. So I'll just copy down what's there. 2x plus 5 equals 20 minus 3x. And this was given to us. And I'm actually going to copy given over for the reason as well. So that's what we were given. Now for step 2, there's lots of ways that you could continue from here. So this is just one way of solving it. So if you did this on your own, what you have might look different than mine. But as long as you end up with the same answer, and as long as all the steps along the way are valid steps, that's fine. So this is just one way of doing it. So in solving an equation like this, what we want to do is try to get everything with an x on one side, try to get everything without an x onto the other side. So what I'm going to do is I'm going to add 3x to both sides. The reason I can do that is the addition property. So what that's going to look like if I add 3x to both sides, when we combine like terms, we'll get 2x plus 3x is 5x. And then on the right side, the negative 3x and positive 3x will cancel each other out. Now for step 3, what I'm going to do is I'm going to subtract 5 from both sides. And the reason I can subtract 5 from both sides is because of the subtraction property. So what that'll look like on the left side, the positive 5 and negative 5 will cancel each other out, just leaving 5x. And then 20 minus 5 is 15. The next thing I want to do is to get that x by itself, divide both sides by 5. And I can divide both sides by 5 because of the division property. So when I divide both sides by 5, I get x equals 3. Now, this may seem tedious and longer than it needs to be, and in this case it is, but we need to get used to thinking in this way in terms of having very, very structured thinking and going through step by step and making sure that every single step as we go from one thing to the next is laid out in the most clear manner possible so that there's absolutely no ambiguity about what we're doing. This is how we prove things in mathematics. We have to be as clear as we can possibly be about what we are doing. So if we're going to prove that something is true, we need every single step laid out perfectly and clearly so that anyone looking at it can follow along and go step to step to step and be utterly convinced of how we got from the beginning to the end. All right, let's keep going. So another property that we have is the distributive property. So what we can do with, if we have A outside of parentheses and B plus C inside parentheses, we can multiply A by both things in the parentheses and then add those together. So we get A times B plus A times C. So we're going to use this property in the next proof. So we'll start with the given again. What we're going to do next is distribute -4 through the parentheses. And the reason we can do that is because of the distributive property that we just talked about. So in step number 2, that's what you get when you distribute the -4 through the parentheses. After that, what we need to do is try to get everything without an x all on one side of the equation. So we've got numbers on both sides of the equation. We need to fix that. So to do that, we can add 8 to both sides. And the reason we can do that is because of the addition property. And once we've added 8 to both sides, then we have what we need in order to solve. So it just takes one more step here. We've got -44 times x. To get rid of that, we're going to divide. So if we divide both sides by -44, that will solve the equation. And there you have it. So we can divide both sides by -44 because of the division property, and that gives us x equals -2. All right, example 3. When you exercise, your target heart rate should be between 50 to 70% of your maximum heart rate. Your target heart rate, R, at 70% can be determined by the formula R equals 0.70 times the quantity 220 minus A, where A represents your age in years. Solve the formula for A. So in this one, we're just going to rearrange the formula. So we can't actually get a number for A, but we can rearrange the formula. So we're going to start with the givens. Right now, A is in parentheses, so we need to find a way to get rid of those. So what we can do is we can distribute 0.7 through the parentheses, and that'll allow us to then rearrange the equation to get A by itself. So we're going to distribute that 0.7 through the parentheses, and that we can do that because of the distributive property. Now that we've distributed 0.7 across the parentheses, to get A by itself, we want to get rid of that 154. We want to get that to the other side. So let's subtract 154 from both sides. And we can do that because of the subtraction property. And the last thing, if we're trying to solve for A, we want to get A by itself, we're going to have to get rid of that -0.7. Since it's multiplied by A, we're going to have to divide by divide by -0.7. That will get A by itself. And the reason we can do that is the division property again. When you divide -0.7 on both sides, make sure you be careful about your signs. So we'll flip the sign of each term, and also make sure you divide both things on that side by -0.7. You need to divide the entire side by 0.7. I see a lot of students when they get to something like this either only divide R by -0.7 or only divide -154 by 0.7. You've got to divide the entire side of the equation by that number, so be sure to do that. We're going to look at some more properties. These properties are true for all real numbers, and also kind of lengths and measures. So the first property that we're going to look at is called the reflexive property. So a good way to think of the reflexive property is much like a reflexive verb in English class or language class. So a reflexive verb is something you do to yourself. In mathematics, when we're talking about the reflexive property, we're saying that something is the same as itself. Now this may seem like a very trivial thing to say, that A is equal to A, but we do need to have, again, when we're doing proofs, we need to be very, very clear about what we're saying and make sure that every single thing that we do is justified. And there are times when we need to use the reflexive property, when we need to justify something by saying, well, something is the same as itself. If we're talking about segment length, remember that segment length is, the notation we use for that is just the two letters at the end of the segment, just written next to each other. That means the length of the segment. So when we just have AB written there, we can say that's the length of AB, and we can say that it is the same as the length of AB. It's the same as itself. If we're talking about angle measures, so how many degrees an angle is, we use the notation with the m in front of the angle, so that means the measure of angle A. And so we can say the measure of angle A is equal to the measure of angle A. Next property we're going to look at is the symmetric property of equality. So basically what this one says is that if you take an equation and flip it around, so take the left part and make it the right part, and take the right part and make it the left part, you still get a true statement. So if A equals B, then we can say that B equals A. There's no difference between saying that A is equal to B and saying that B is equal to A. Again, seemingly a trivial thing, but we've got to justify every single thing that we do in mathematics. So segment length, we can do the same thing. We can say, if we can say that the length of AB is equal to the length of CD, then we can say that the length of CD is equal to the length of AB. Same thing with angles. We can talk about measures of angles. So if the measure of angle A is equal to the measure of angle B, then the measure of angle B is equal to the measure of angle A. And then we get the transitive property of equality. So this one uses kind of substitution, the substitution property we were talking about before. So if we have A is equal to B and B is equal to C, well, if you imagine substituting one of those equations in for the other, so maybe we take, since B and B are in there, we can take A and just substitute it in there for B. And so we can say then that A is equal to C. This is what the transitive property tells us. So if you have one thing that is equal to another thing, that second thing is equal to a third thing, then the first and third things have to be equal to each other. We can say the same thing about segment length. So if the length of AB is equal to the length of CD, and the length of CD is equal to the length of EF, then the length of AB must be equal to the length of EF. And the same thing for angle measures. So if the measure of angle A is the same as the measure of angle B, and the measure of angle B is the same as the measure of angle C, then the measure of angle A must be equal to the measure of angle C. All right, let's use some of these. Example 4. You are designing a logo to sell daffodils. Use the information given. Determine whether the measure of angle EBA is equal to the measure of angle DBC. Okay, so we've got this picture, and then we've kind of translated this into geometric language where we've got points and angles labeled on it. All right, so we know that the measure of angles 1 and 2 there are equal because they are marked congruent. So there's this little red marking right here and right here. So that tells us that those two measures are equal to each other. All right, well, we've got in the middle this measure right here. So if we look at these two angles, if you don't see, the two angles we're looking for are EBA, so that's this angle here, and then also DBC, which is this angle here. So you can see that both of those angles have the green part in it, and then the other part of the angle is, for each of them, that red piece on the side there. So they both share that green part, and then they each have the red part, but the red parts are congruent. So if they share the green part, and then the other part of each angle is two pieces that are congruent, then yes, they must be the same as each other. They must be the same angle, because one part is shared, and the other part is the same as each other. All right, in example 5, the length of segment AB is the same as the length of segment CD. So that's already marked on the picture. That's what this mark here and this mark here mean, those two vertical marks on AB and CD. That means that they are congruent. Show that AC is congruent to BD. All right, well, we have the same exact argument as we did for the angles in the last one. So if we look at AC, and if we look at BD, those share BC. So BC is obviously the same as itself. And actually, I'll write this one out. So we know that AC is equal to BC plus AB. So if we take segment BC, so that's the middle one, and then add AB to it, that's this side one, so BC is this length here. If we add to it AB, then we'll get AC. All right, well, we can do the same kind of thing for segment BD. So we know that BD is equal to segment BC plus segment CD. So if we take segment BC and then add segment CD to it, we will get the same thing. We'll get BD. So then what we can look at is, well, BC is the same as BC, and then AB and CD, well, that's these pieces that are marked congruent here. So these are also the same. So we have BC, which is the same as itself by the reflexive property, and AB and CD, it's told to us that these are the same. We're given that. And so yeah, AC and BD, they have to be the same.